Chapter 12, Deflection of Beams and Shafts, Moment Area Theorem, Part B of Chapter 12, example number 4. So let's see what do we have for this example. So if we do have this time we do have a two fixed support beam of AB. It's fixed at both ends and handling a concentrated load of P like previous problem, which we had a concentrated load applied to a two simple support, this time a two fixed support at both ends. So definitely we do know we do have a moment back there. So if there is a moment at A because of fixed support at A, and there is a moment at B due to fixed support at B. And just by a guess, due to symmetry of structure, one can guess M at A should be identical to M at B, which is correct, and we will verify that in later on. So solution based on moment area. So it just says if you want to know what delta maximum is, so if you just draw M over EI. So moment, it's a simple enough because just consider forget about a two fixed support, and it just consider a uh, concentrated load applies at the center of two simple supports. So like previous problem, we do have a moment of a PL over 4EI and no nothing if it's simple support at both ends. So that's a 0, that's a 0. Then apply the effect of MA. So that's the moment pulls the top, it's a negative moment. So that's why we are just climbing down by the moment of A. So that's the amount of MA. So that's MA over EI. Then no nothing at the traveling from no other moment from A to B, and all of a sudden a MP. So that's the addition of these two shapes give us the area under moment. So this is a negative one and that's a positive. Hmm? And if you look at the geometry of the structure by having a concentrated load applies at the center of a two fixed support beam of AB, you can easily see uh, we don't have theta at A, that's 0. We don't have delta at A, that's 0. We don't have theta at B because it's fixed, we don't have delta. But the maximum deflection due to symmetry happen at center, and that's delta maximum. And if you have a closer look, a delta max, again, this distance is equal to this a green distance, and that's the green vertical line, and that's nothing but tangential derivation of a point A with respect to a horizontal line at C. That's a tangential derivation of A with respect to C. And that's again a second moment area theorem. So it just says, and again, that's M over EI. That's M over EI between, that's equal to M over EI between point A and C times x bar, and x bar is just measured from first point, first component. So that's A. So that's x bar for the top part, centroid to A, and for the other part, it's just centroid of a half of the area. And we can also consider, due to symmetry, we can consider the half of area, then multiply it. And also, we just need to go through the center. So we need this area. So how that goes, let's proceed to solve the problem. And at the same time, before solving the problem, a golden key of the problem is that we do know Before doing anything, we do know theta A with respect to B is 0. So theta A is 0, theta B is 0, theta A with respect to B is 0, and theta is area under moment from A to B. So how that goes? That goes 2 of this area, 2 of this area, and that's a half of triangle at the top, PL over 4EA times L over 2, which is the half of the length, plus a 2 of this, and that's MA over EI, and we don't know what that is. We do not know what MA is, but we do know that's the area under M over EI for negative part times, mhm, uh, again, that should be L over 2. So let me modify that. That's 2 of M L over 2. That's because that's L over 2. And if you do the math, it gives you a MA is equal to a PL over 8EI, and negative is just about the direction which is consistent or inconsistent with your original direction. So the numeric value for moment is PL over 8EI, and that just says if you want, now you know what the moment is, and this time TA with respect to C, it just goes by a area, positive area times 2/3 of L over 2, and a negative area by times L over 4. So that's a half of PL over 4EA times L over 2. That's the area, and that's the distance, 2/3 of centroid, plus MA over EA times L over 2 times the distance of centroid to A, centroid to A, centroid to A. That's TA with respect to C. And this time we do know MA is a negative PL over 8. So that's, if you do the math, it just gives you TA with respect to C, which is a delta maximum, is PL cubed over, sorry, PL cubed over a 192 EI. There is no theta, there is no theta due to fixed support, and that's with a 2 step we can get delta maximum for a 2 fixed a simple support, and that's to my understanding is a one of the easiest approach of calculation based on first and second moment area theory. So it says if you have a 2 fixed and support uh, handling concentrated load of P at its center, it just have a delta maximum PL cubed over 192 EI delta max, which happens at the center. Mhm. That's delta C. And TA is equal to TB. That's 0 because it's fixed. And at the same time, the numeric value of the moment at A is PL over 8, identical to MB. That's PL over 8. We'll solve more examples in next videos. Thank you.